Right, so for this presentation, I'll first motivate why we actually want to do this, or why do we want to generate next step hints for task-oriented programs. And then I'll explain what task-oriented programming is, what symbolic execution is, and how we married it to generate next step hints. All right, so let's see if this works. Yeah, great. So almost every business and institution nowadays automates their processes, automates the stuff that they have to do. So behind me you see a few of the people that we work with. So we see the Coastal Guard, and they actually use a workflow system to monitor incidents at sea and how they should respond to that. And this allows people to collaborate, so it allows the first responders to work with each other. And next to that you see a hospital. This is a cow, a computer on wheels. I guess you've seen it. And they also use a computer system that has information about the patients that are in the hospital and the treatments that they have. And it allows the doctors and other healthcare professionals to work together in helping the patients get better. And then here we have the Dutch tax office, which has automated almost every part of the tax administration. And citizens can even use an app on their phone now to hand in their yearly tax report. And next to that, we see the Netherlands Royal Navy. And they, of course, also have a lot of software on their ships to track anything from radar to command goals that they might have. And all of these systems are very similar, and we consider them workflow systems. So what is a workflow system? Well, a workflow system is a system that has some representation of the domain. So if you're in a hospital, it has the information about the patients and the treatments and stuff like that. And there are some processes that can be performed that alter the data in the system. So a doctor can start up a new treatment, and then there are steps in that treatment which change actually the data in the system. And of course, this is all to facilitate people working together. So that's the goal of a workflow system. So I guess I clicked one too much. So it could be the case in a workflow system that the people have to make a choice, right? So if you're a doctor, you have to pick a treatment for the patient. If you're at the Coastal Guard, there might be an incident. What will you do? So for this, you use a decision support system. And the idea of a decision support system is that it has some kind of, let's see if this works, some kind of model of the problem, which is obviously smaller than the actual workflow system. And it has a reasoning engine that takes data from the workflow system together with that model, and then comes up with some sort of advice for the end user. And this is great. Research has shown that having a decision support system greatly improves the quality of the decisions that are made. It improves the speed with which decisions are made. And of course, this increases the productivity of the company or the. But developing a decision support system is expensive. I mean, you already have developed the workflow system, and now you need to come up with a different model for your decision support system. And once you have that system and you change something in the workflow system, this means that you need to update the model as well. So what we want to do is we just want to get rid of the whole model, and that's why we want to generate automatic hints using symbolic execution. All right, so now I'm going to explain a little bit about task-oriented programming. So this is work that I did together with my colleagues from Radboud University. And as I said, these workflow systems are very similar, right? I mean, they all have a representation of the data. They all have flows that can be applied to that data, and they allow people to work together. So why would you develop such a system from scratch every time? And of course, we would make a domain-specific language for this. And that's the idea behind task-oriented programming. You have a few basic building blocks that completely describe the workflow system, and from that You actually generate the whole application. And here behind me you see the 3 basic building blocks of task-oriented programming. The most basic thing that you have are editors, and this is the point where the user interacts with the system. So this is where the user clicks on a button or enters in a value, or maybe drags even a marker on the map, anything that you can think of that, inputs data or changes data from the system. And then we have combinators that describe how these actions follow up onto another. So this is really how, this defines how people actually collaborate with each other. And this is based on all the common workflow patterns that are identified in previous research. And then, of course, we also need the representation of the domain, and this is done by shares, which can be accessed by the editors. And the most used implementation of task-oriented programming is called iTasks. So how many of you are familiar with iTasks? Okay, a few. So when we started doing this research, the problem that we ran into is that iTasks is only defined as a reference implementation. There is no formal semantics for it. And the things that we wanted to do required that we made one. And this is where Top Hat comes in. And Top Hat has this task layer embedded into the simply typed Lambda calculus. As you see behind me, this is all very standard stuff. And in the last line, you see references, and this is how we accommodate the shares in Top Hat. And then on top of that, we have the task layer. And the most basic tasks, as you remember from a few slides back, are the editors. And in Top Hat, there are 3 kinds of editors. We have an editor that has a certain value in it, an empty editor with a type, and we have an editor that points to a share. And there are 3 actions that the user can do. The user can, in case of a valued editor, update this value, and then we get back an editor containing a new value. If the editor is empty, we can enter value into it and we get a valued editor back. And in case of a shared editor, the user can send a new value, and then this value is put into the state, and the same editor is returned because it points at the state, of course. So if you render it, you just read from the state. Now, this won't do us much good if we don't have the combinators, right, that combine these editors into bigger tasks and smaller tasks into bigger tasks as well. And the most basic combinator that you can think of is performing 2 tasks in sequence. And this is what the step combinator does. So we have a task on the left, and on the right we have an expression that takes a value and then produces the next task that we'll work on. And then the user can either send input to this left task, and when the user is done, he can send a continue event, and then here we calculate the value of the first task, and then we calculate with that the next task that we're going to work on. We can also do stuff in parallel. Oh, I guess I shouldn't use this thing anymore. All right. So we can also do stuff in parallel, of course, which means that we can either work on the left task or the right, and we can send those events to this task. So if we send a first and then an input, we just propagate it to the first task that we have. And the last editor that we have is a choice combinator. And this choice combinator allows users to choose between a left or a right task. All right, so this looks very simple, but this actually allows you to describe real-world collaboration that we see in workflow systems. And to sort of make this live a bit more for you, I'll give a small example. So imagine that you are a tax office and you need to handle subsidy requests for solar panels. So if you get solar panels on your roof, you can get some money back from the government. Of course, there are a few constraints. You need to apply for the subsidy within 365 days of installation, and an installation company needs to actually confirm that they were at your house. And then you need approval from the tax office, and you can get at most a subsidy of 600 euros. And when we implement this in Top Hat, it looks something like this, where here in the red box, we have in parallel the citizen providing documents, the company confirming, and once those two tasks have been completed, we'll go to the tax officer with that information, and the tax officer can approve or deny this request. And in the end, we return the subsidy amount that was calculated in between the two boxes. So as you can see, with this very simple language, you can express all kinds of workflows immediately. So this was a crash course basically on Top Hat. Now that we have our language, let's talk about symbolic execution. So, the idea of symbolic execution is that you want to predict the behavior of a program without actually knowing what the input will be. So in the case of Top Hat, the input is what the users put into the system. So these are the things that we are going to simulate. So behind me you see a very small example where the user can input two integers actually, and then we have an if statement that checks if the first input is larger than the second, then we get back a tuple containing the second and the first, and otherwise the first and the second. And what we can now do is we can symbolically execute this program by entering symbols in place of the inputs that we have there. And this will result in two symbolic runs. In the first one, we record that we have a path condition that S1 must be larger than S2, and we get back S2 and S1. And in the other case, we record the path condition S1 is smaller or equal to S2, and we get S1, S2 back. So this is literally the then and the else branch. So why does this help us? Well, now we have a complete description of what the program does result-wise. And now we can say stuff about the results of this program. So let's say we want to prove that no matter what the user input is, we always get back a tuple where the first element is smaller or equal to the second, which is defined as this property here. And now we can just simply input the symbolic runs into that property, and we can verify for both runs that this is true. So that's why we want to do symbolic execution, because we now can prove that properties always hold over our Top Hat programs. So how do we go from the normal semantics that we had for Top Hat to the symbolic one? Well, before we had the user input, but at this point we don't know the user input. That's what we want to simulate. So instead, we generate a symbolic input and a path condition for that path. You remember before we saw that depending on the user input, we can either take the then or the else branch. So that's why we need a path condition. And you'll also notice that there's a line above here, and that indicates that this is a set, because we can, of course, have multiple results, as you saw in the example. So now diving into the semantics, what do we do with the editors? So before we had an actual value from the user, but now we don't have that. So we'll generate a fresh symbol, put that into the editor, return it, and record the path condition, in this case true, because for an empty editor we can always generate a symbol. All right. And more interesting is the if then else. So before we used to just evaluate the condition here, E1, and we get either true or we get false, and then we calculate E2 or E3. But because we are now in the symbolic world, we don't know what the actual result will be of the evaluation of E1. So instead, we'll take both branches. So we calculate E1, which gives us a symbolic result. Then we'll calculate E2 and E3. And we say we can have result V2 if V1 is true, or we have V3 if V1 is false, actually. And the same is true for the pick combinator, where the user can choose the left or the right task. Before we had an actual input left or an actual input right, but now we don't. So we take both, and then we record here that we saw a symbolic input L and here symbolic input R. So this describes the symbolic semantics, but there's one step that we still need to take. Our goal is to take, oh yeah, there's a question.
What's the role of this negation of autocorrected head?
Here, yeah, that's a good point. So we only allow users to step to a certain task if it's not failing. So we introduce the concept of failing to disallow certain steps in the program. As a programmer, you can use that. So you can, for example, check if a value is true that the user input, and then if it's not, you can prohibit them from stepping so that the user can update the value. Does that make sense?
Yep.
All right, thanks. Oh yeah, so now we have our symbolic semantics, but our actual goal is to run whole programs and then to arrive at a set of symbolic executions for that program. So we still need to define that. So as I said, we have our program, and then we return the set of symbolic results, and actually the list of symbolic inputs that we need for that result, together with the path condition that must hold. And to build this, we simply run the symbolic execution semantics until, at some point, we arrive at Tn, and Tn has a certain value, and then this is just a list of inputs that we've seen, and these are all the path conditions. All right, so now going back to the solar panel example, let's verify this. So remember, we have a few requirements for this program. The citizen needs to apply within 365 days. We need confirmation from the installation company, and we require approval from the tax office, and we can get at most 600 euros. And when we turn this into a property for this program, it looks something like this. So the subsidy amount is only larger or equal to 0 if we have confirmation, and it's only larger or equal if we have approval from the tax office, and we can only have approval if we have confirmation and if we were on time with our application. The subsidy amount shouldn't be larger than 600. And of course, if we don't have approval, we should have 0 subsidy. Now, to verify that this property holds, we just symbolically run the program that we saw before, and we get something like this. So in the first column, we see the symbolic results. Then we see the symbolic inputs that were needed to arrive at that result, and the path condition that must hold. And in order to verify that our property holds, we just check for every symbolic run that indeed the property is true, which it is, fortunately. So yeah, that's all there is to symbolic execution for Top Hat. We have our simulation function, and we can prove it. Yeah?
I'm not sure, do you also discard infeasible paths when you during the evaluation of the properties you
Yeah.
find something is a contradiction?
Yeah, that's a good question, actually. Let me see where I have that. Yeah, so I didn't show it on the slide here, but during these steps, we check if the concatenation of these path conditions is actually feasible. Yeah, so we use a set solver for that in the Haskell implementation that we have of this system. Yeah, great question. Any other questions at this point? Yeah.
Is the number of paths you get sort of exponential in the size of something like that?
Yeah.
Doesn't this become infeasible quite quickly?
Well, that's a good question. So we don't have loops. That helps. Yeah, I mean, if you build a large workflow structure, then stuff gets very complicated very rapidly. Yeah. But I think that, so of course this is for a theoretical system, Top Hat, and I think if it would be interesting to apply it to like iTasks or a big workflow language. And I think workflows are suitable for this because they are very simple usually if you look at systems that are used in practice. So there are not many things in parallel. There are just a few steps usually in every workflow that you see. Great question, thanks. Any other? All right. So now we get at the heart of the presentation. How do we now generate next step hints for these programs using the symbolic execution that we just saw? So let's start with an example program again. So this program is supposed to be a vending machine. So the editor for the integer simulates a coin slot. So the user can input coins. This is represented by a value here. And then when the user is done, he can press continue. And then if one coin was inserted, we get a and if and in that case, the user should edit this value again to either be 1. He cannot make that step until the next task. So we just now run it symbolically again. The first one is, so we input a symbol here, S, and then we have a path condition S is 1, and in that case we have a biscuit. If S is not 1, then S can be equal to 2. In that case we get a granola bar. And if S is also not 2, well, this case cannot happen as I explained, because then you go back to this original task. Say our goal is to get a granola bar, and we can define it like this. So we have a function that takes the symbolic value and then compares it against our goal, which is the granola bar. What we now do is then we take this, for every symbolic run, we take this function, we input the symbolic result, and check if that together with the path condition is true. So for the first run, we get S must be 1, which is true, and then biscuit is granola bar, which obviously is true. But in this run, we have, fortunately, so S is not 1, S is 2. Well, this is satisfiable, and this is, of course, true. So great, we can tell the user, input 2, and you will get a granola bar. So that's really the basic idea of how we want to generate hints. All right, so but how do we now actually define the function that calculates these hints for us? Well, obviously, it is based on the symbolic execution that we saw here earlier. So we have our program, and we get a set of symbolic results. And we want to have a function that looks like this. So it takes a task and a state, and then the goal function that we saw earlier, and then it calculates a set of hints, which a hint is just an input together with a predicate. That's the path condition that must hold. So of course, we do the simulation of that task. And as we saw in the example, the path condition together with the goal must be satisfiable. And if that's the case, we just give back the first first input that we calculated here together with this condition that must hold for that hint to be true. So this is in the end what a looks like. We have a symbolic input and a condition over that input. All right, so let's go back for the third time to our text example. So let's say we want to help the citizen. The citizen wants to receive a positive amount of subsidy. Let's generate hints for the citizen. So of course then we look at the result of the task, which looks like this, and we formulate the goal. So this should be larger than 0, which looks like this. So we take the result and then say V, which is the subsidy amount, should be larger than 0. And we run this symbolically, and we check for every actually adheres to this. And obviously it's the first 6 here, for which we can receive a positive subsidy amount. So if you look at these 6, there's some duplicate information in there, and if you filter that out, we finally arrive at 3 hints So either the user can input the subsidy amount, but there's a condition there that must hold in order for it to be larger than 0, or the invoice date can be inputted, or the citizen can just wait for the installation company to say, okay, we were at your house. So a very, very small example to give you an idea of how this symbolic system works. All right, so now we have actually our decision support system that does not need any kind of model. It just takes the complete workflow system and uses that to calculate hints for the end user. Great. But we need to do one last thing. We need to prove that these hints actually make sense, that these hints are correct. And what does it mean for a hint to be correct? Well, if we have our hints function that calculates a set of hints, then for every hint, it must be true that if we actually put it into the system, that at some point after executing a few steps, we arrive at our goal. And also the other way around, if we have a certain input, and after a few steps we arrive at the goal, then this input must be represented by the set of hints that are computed by the hints function. And this is actually proven in the paper. I won't bore you with all the details. All right, so to briefly summarize, we've seen Top Hat and its semantics. We can simulate Top Hat programs. And in the end, we saw how we can compute hints for Top Hat programs.